Hello everyone and welcome to the 2021 Brazilian Power Electronic Conference, COBEP. In this video I will show a paper that is entitled Virtual Linear Process in the Degree of Renewable Energies at University of Chubut with Typhoon Hill Control Center. I am the author, my name is Tulio Hernandez and I am professor at University of Chubut in Argentina. We will be talking about these topics: objective, introduction, the design of photovoltaic single-phase and grid model, a proportional integral current controller schematic, a methodology to obtain the proportional and integral gains through a simple pole assignment technique, a short video where we show the implementation of virtual field SCADA, the results of the virtual laboratory in the students of the University of Chubut, and finally conclusions. The objective is design a model photovoltaic generator single-phase connected to grid model in Typhoon Hill Control Center to develop a virtual laboratory so that the students could have a best professional practice. From 2017, in the University of Chubut, Patagonia, Argentina, began the degree of Technical and Renewable Energies, with emphasis in solar, wind, hydro, and biomass energies, and the students have a profile to solve and management energy in electrical power system of low and medium power capacity. Nowadays, the use of power electronics applied to distributed generation is increasing overall in solar generation, where a photovoltaic panel, inverter, energy measurement, and control and monitor system to supply energy at home and also is feasible connected to the grid. For this reason, the design of a virtual laboratory began in 2020 and it was done in three phases: evaluation, certification, and design. In evaluation, the software Typhoon Hill Control Center was selected because it has multiple advantages in the study of renewable energies, the certification of a professor as a specialist Hill, and finally, the design of model applied to residential lot at Chubut province. For the design of PV single-phase and grid model, as is shown in the schematic, first the PV source. This model of current and voltage and power and voltage curves was done with web form generator toolbox. Its curve PV was based in the value of average demand associated to residential lot at Chubut province. In Now we have the residential lot energy measurement and grid model. The lot was modeled as constant impedance and its values are typical at two provinces. The energy measurement block can obtain the measurement of active power, reactive power, and energy. The grid impedance model as a with grid. The single-phase inverter. The single-phase inverter based in two levels with four IGBT semiconductors. The output has a LC filter with damping resistor to minimize the total harmonic distortions. The control model is illustrated with a maximum power point tracking algorithm, MPPT, DC voltage controller, phase locking loop, solid parallel, active and reactive power control, PQ control, quadrature signal transfer function, proportional integral current controller, and pulse width modulation, PWM. In the In this diagram, two peak contours associated to the rotational frames P and Q are shown, and the output is obtained by the transformation dq to alpha beta. The signal in alpha frame is the input to the pulse width modulator. Together, gains in the frame D and Q are equals. In the pole assignment technique, first we have a closed-loop model of the system with a proportional integral controller transfer function and planned transfer function where the total resistance and inductance are the add of filter and grid impedance in per unit values. The proportional integral gains were set through a simple pole assignment technique. As reference, we have the paper of Chen and Lim, where this technique was applied to a proportional resonant controller. With the characteristic equation and through the pole assignment technique, considering the system with two complex poles that depend on a control variable shift, as shown in this figure of the rule locus of the closed-loop transfer function. In this figure, we can see the curves with different values of proportional gain, integral gain, and frequency versus control variable chi between 10 to 20, and the system data to solve the integral and proportional gains. Design of the panel virtual SCADA has multiple guides with the objective that the students can control, monitor, and set variables, irradiance, temperature, current, voltage, frequency, load management, active power, and reactive power. On this video, we can see the model did in a schematic editor. The PV model, the schematic is validated and compiled. After, you can load a virtual hill model in the hill SCADA panel, where the student can monitor and control variables such as irradiance, temperature, logs, switch, and in the case of transit studies, uh, they have the scope capture with trigger. For example, in this case, when the water heater is on, you can view the current grid signal to check the performance of the proportional integral controller. A virtual laboratory was done with the following list of cases, which were included in the virtual laboratory guide. In the case 1 is a nominal X scenario with solar irradiance equal to 1000 watts by meter square and ambient temperature equal to 25 degrees Celsius. In the case 2 is a summer S scenario. In this case, the solar irradiance is equal to 800 watts by meter square and ambient temperature equal to 30 degrees Celsius. And the last scenario is the winter scenario with solar irradiance equal to 4,000 watts by meter square and ambient temperature equal to 5 degrees Celsius. In this table, we can the results of the laboratory where for each case where the students takes input and output inverter voltage and current, PV active power, point common coupling, active and reactive power to generate a report if it has some unstable signal. It was described on the report. For example, in the case 3, a maximum voltage drop was 19% nominal voltage. This value is out of the limit established in distributed generation law of Argentina. Finally, the conclusion for this paper were in the degree of renewable energies at University of Chubut, a virtual laboratory has been developed, employing an improvement on the learning process. The design was based on the energy resource and weather of the province of Chubut in Argentina. A model in Typhoon Hill Center Control was made with multiple advantages, such as the feasibility of control monitor and set equipment associated with a PV source. Thank you everyone, and if you have any question about the model, I'd be happy to answer them by email.